Hello, my name is Timothy Hamilton. I am the Enterprise Manager for Multiplanetary INnovation Enterprise, also known as MINE, and we seek to design, test, and implement robotic technologies for extracting and using local resources, construction, and characterization in extreme environments. These environments currently include lunar, Martian, and flooded subterranean environments on Earth. Mind works in multidisciplinary groups to develop technology to perform tasks in extreme environments on Earth and on other planets. The Enterprise is currently working on four different projects: Lunabotics, Diver, Adaptive Boom Arm, and Trencher. This year we will be focusing on the Trencher project but giving a brief overview of the other projects. The Enterprise currently has 41 members from various majors and specialties. Each of these teams have put in a lot of work this semester, and I'm excited to showcase all of their hard work.
Hi, I'm Gabe Ellis, co-leader of the Deep Investigation Vehicle for Energy Resources team, also known as Diver. Diver stands for Deep Investigation Vehicle for Energy Resources, as I mentioned earlier. It focuses on making an untethered ROV to explore and map flooded mines, with the specific goal of exploring Quincy Mine. Our goal is to collect data for those interested in the possible implementation of a renewable energy resource within Quincy Mine, specifically geothermal or hydroelectric power. To accomplish this, we use a combination of sensors as well as an integrated hardware-software design to collect data such as temperature and pH while simultaneously mapping the mine. The physical design of the ROV and the placement of its center of gravity is critical to its submerged operation. This project is one of the first of its kind, tackling the relatively new challenge of repurposing mine shafts. The uniqueness of this project allows members to be especially creative in overcoming the challenges presented.
Hi, I'm Chuck Carey, lead of the Lunabotics team, currently MINE's largest project team. Over the last 3 years, the Lunabotics team has been participating in NASA's annual robotic mining competition. Competing with teams from 50 different universities across the nation, this project focuses on designing, manufacturing, and testing a lunar rover. This rover needs to be capable of excavating and transporting simulated lunar ice, a valuable resource which can be used to create rocket propellant and support human life on the moon. The robot will interact with lunar regolith, a fine substance that presents additional challenges to system mobility, mechanical wear, electrical heat dissipation, and more. To meet the expectations of the competition, the Lunabotics team has elected to use a systems engineering approach, breaking the project down into several subsystems. These include the chassis, hopper, excavation, electrical hardware, software and communication, and system integration teams. The Lunabotic project gives students valuable experience with complex engineering in the rapidly expanding space industry.
Hello, I'm Colin Miller, the team lead of MINE's Adaptive Boom Arm project. For the past 2 semesters, we've been working on a specific design challenge provided by our industry sponsor, JLG, who are a leading manufacturer of access equipment. JLG recruited our team to design and prototype an adaptable boom arm that is able to maneuver around obstacles. Due to this project being under a non-disclosure agreement, we are unable to go into specific details of our solution. However, we can present an abbreviated synopsis of our work. To begin, our group brainstormed multiple novel solutions to the specified project, and then used the Pew analysis strategy to narrow down the options until we arrived upon the most optimized design. After that, we began to simultaneously work on a full-size CAD model and a scaled-down physical prototype, so that we could most accurately demonstrate our design's efficacy to JLG.
With the Artemis program, NASA aims to send astronauts back to the moon by 2025 and establish a permanent human presence. Building the necessary infrastructure to complete this task will require an abundance of resources. Because of the high cost of launching supplies from Earth, efficient and inexpensive processes need to be developed to take advantage of the materials available on the moon.
With these challenging goals steadily approaching, NASA has been working with contractors and universities to make this mission a reality. The Lunar Trencher is an enterprise project within the Multiplanetary Innovations Enterprise at Michigan Tech that aims to provide a proof of concept of extracting the lunar surface with a bucket ladder style excavator. Bucket ladders offer a continuous method of excavation that can transport a large amount of material with minimal electricity, an important consideration for operations on the moon. With bucket ladders, NASA will be able to extract icy regolith to create rocket fuel on the moon and have a reliable method to shape the lunar surface. The Lunar Trencher team is currently testing a custom-built bucket ladder to obtain usability, power, and wear data in simulated lunar regolith. The team also has plans to test the bucket ladder in vacuum conditions to gather important data for future designs that may be used on the moon.
To accomplish these mission goals, the Trencher team, currently composed of 9 undergraduate students, has modified the Trencher for vacuum testing and aims to achieve a rating of 6 on NASA's Technology Readiness Level, or TRL 6. This means the system must be tested in a simulated lunar environment. Before the team could perform the required tests for TRL 6, we first had to prove that the Trencher was operable at atmospheric conditions. This was done using a sandbox and regolith cart from Michigan Tech's Planetary Surface Technology Development Lab, or PSTDL. The team also had to make additional modifications to the Trencher, such as creating a gantry system, adding a chute, and modifying the Trencher electrical systems.
The Trencher is composed of 5 subsystems: communications, drivetrain, frame, testing equipment, and buckets. The frame is the mechanical body of the Trencher, which includes the mounts for drivetrain components and the regolith chute. The drivetrain consists of the components that drive the buckets. The mechanisms used to move the mechanical assembly of the Trencher are referred to as the testing equipment. This includes the FANUC robotic arm as well as the Dusty Thermal Vacuum Chamber, or DTVAC, which is housed in the Benedict Lab within Michigan Tech's Minerals and Materials building. The Trencher was tested using our custom-built gantry system. Finally, the communications subsystem controls the drivetrain and the gantry system and also handles the acquisition of power data for the Trencher.
Testing and data collection began in earnest during the 2021-2022 school year. The team first tested their ability to use the Trencher in a sandbox environment. Once the Trencher was moved to the DTVAC regolith cart, power consumption was then recorded. The project aims to record electrical consumption to determine if it is an effective and efficient excavation tool for a lunar environment. To do this, we have isolated the current draw on the Trencher motor from the drivetrain and testing equipment to determine the pure electrical usage. Vacuum testing to simulate lunar conditions will be done using MTU's DTVAC, which can achieve 1 microtorr. The team is also testing wear and tear on the bucket ladder system at atmosphere and vacuum to evaluate the long-term reliability of the system.
As the semester comes to an end, the team hopes to perform an additional DTVAC test to obtain more useful data. Next fall, the Trencher team will return to Michigan Tech and implement a vertical motion stage to the gantry system. This will give the Trencher the ability to make multiple passes during a single test, making each test more efficient and informative. Once DTVAC testing is completed, the team will transition to attaching the Trencher to the PSTDL's field rover. This will be used to more closely simulate real-life use of the Trencher through testing at the Keweenaw stamp sands. We would like to thank our sponsors at GM and our advisors at the PSTDL for the support they have given us. Thank you for watching.